Welcome to today's lecture. Today we will be working out a problem from the topic moment of inertia, and it is coming under the subject engineering mechanics. So moment of inertia, problems on moment of inertia can be asked in two ways. One they will give a figure and they will also provide an axis. So in this figure you can see we have an x-axis and y-axis, and they will directly ask to calculate the moment of inertia of the composite section about x-axis or y-axis or both. In another case, what they will do is like they will simply give a figure and they will ask us to find out or work out the moment of inertia of the composite section about centroidal x-axis and centroidal y-axis. So in that type of problem, we have to initially calculate the centroid, that is the value of x bar and y bar. Then we have to work out moment of inertia. But in the first case, we need not work out the value of x bar and y bar. So we have such type of problem. The second type we will discuss in a different lecture. So here we will be focusing on this particular problem. So here we are supposed to calculate the moment of inertia of an angle section. So this is the angle section about the x and y axis, which is shown in the figure. And we have section and the dimensions are given to you. So the base dimension is 10, and this side we have a rectangle which is having a height of 8 centimeter. And please note the width of this bottom rectangle is also given, that is 2 centimeter. The width of the top rectangle is also 2 centimeter. So how we should start? We have to first of all split the given L section or angle section into two simple shapes. We can easily split into two rectangles as we have seen here. And I am taking the bottom rectangle as my first one and the top rectangle as my second one, so that the centroid of these rectangles can be also marked. The centroid of the first shape is marked as G1 and centroid of second one is marked as G2. I hope you remember. So what will be the distance from the left side to this point? It will be base by 2. And what will be this vertical distance? It will be total height by 2. Similarly, for this rectangle alone, if you see, the distance from the left side to this point will be this total width by 2, and from this bottom, that is from this dotted line to this G2 point, what will be the height? It will be 8 centimeter divided by 2, the height of the rectangle divided by 2. Now let's try to see things. So here initially what we are doing is we are calculating the area of each of these shapes. So first one is rectangle, so length into breadth, A1 is equal to 10 into 2 and A2 is equal to 8, height into this distance 2, that is we are getting as 20 and 16 centimeter square respectively. Then what we are doing, we are calculating the value of x1 and x2. And what was x1 and x2? x1 means the horizontal distance that we have to travel from our reference y-axis to the centroid of my first figure. So we have the reference y-axis here. I have to travel a distance of 10 by 2 so that I will reach G1. So you can see here they have written 10 by 2. And what about x2? The horizontal distance I have to travel from my reference y-axis to point G2. That will be, the total is 2. Therefore, this distance is 2 by 2. That will come as 1 centimeter. So that is also written here. Similarly, what will be y1 and y2? In this case, total height divided by 2, that is 2 by 2, 1. So we have written it here. In this case, what will be y1? And please be careful. In this case, don't write y1 as 8 by 2. It is not 8 by 2 because our reference x-axis is at the bottom. So we have to take the vertical distance from the bottom reference axis to this point. That means it will be actually equal to 2 plus 8 by 2. 8 by 2 means this is the distance 8 and 8 by 2 means this will be the value. This distance will be the value from this dotted line to G2. But what we need is the distance, vertical distance from our reference x-axis to point G2. So that it will be 2 plus 8 by 2, which will come as 6 centimeters. Now, how we can calculate the moment of inertia of a composite section about a reference, about a given axis? So what we have to do is like we already have learned some equations by which we can work out the moment of inertia of simple shapes about its own centroidal x-axis as well as centroidal y axis. So for example, if you take the first rectangle, our centroid is G1. I can draw a horizontal axis here, which will be the centroidal x-axis of this rectangle. How can I calculate the moment of inertia of this rectangle about that x-axis? We know the equation b h cube by 12, where b is the base width, that is 10 into 2 cube divided by 12 will give me the moment of inertia about this x-axis. Similarly, I can calculate the value of moment of inertia of this rectangle about centroidal y-axis. And the same procedure can be repeated for my second rectangle or any other figure I have in my question. Now, what we have to do is, if you want to get the total moment of inertia of a composite section about some axis, it will be the sum of contribution of moment of inertia from all the simple shapes. So as we have explained, suppose you want to calculate the moment of inertia of this total shape about the centroidal, not the centroidal, about the given x-axis, it will have contributions from this first figure as well as second figure. And if you consider the x-axis of the centroidal x-axis of first figure, we can calculate the moment of inertia of this figure about that axis, and that will have some contribution to the final moment of inertia about the main x-axis. Similarly, we will have contribution from the centroidal x-axis of my second figure also, and we will see how to work it out. And for calculating the contributions or to transfer the moment of inertia from this centroidal axis to another axis which is parallel to that, we will be using the theorem parallel axis theorem. And what was parallel axis theorem? Suppose we know the moment of inertia of a shape about its own centroidal axis, then we can transfer this moment of inertia to another axis which is parallel to this axis. So as an example, we can take, we have the centroidal x-axis and we know that 10 into 2 cube by 12 is the moment of inertia about this axis. We can transfer that moment of inertia to another axis, that is x-axis. Again, this axis should be parallel to the centroidal x-axis. Okay, so if you want to transfer that, what you have to do? It will be the sum of this moment of inertia. If Ig is the moment of inertia about centroidal x-axis, then Ig plus area of this figure into the distance between these axes square. So Ig plus A into h square. So in this case, what will be Ig? It will be 10 into 2 cube by 12. And what will be A? It will be A1, that is 10 into 2. And what will be H? H will be this distance. In this case, it is our Y1 itself. So that the value will be Ig1xx, that is the moment of inertia of this first figure about centroidal x axis plus area of this figure plus into this distance square. So that is what written here, Ig1xx plus A1 into Y1 square. Why I have, instead of H, I have put here Y1, because in this particular case, H, that is the distance between the centroidal axis and the axis to which we have to transfer moment of inertia, is coming as Y1 itself. That is why I have substituted it like this. And in addition to this, we will have some contribution from the second figure. For that also, we can apply the parallel axis theorem. So if you take the centroidal x-axis, the value of moment of inertia of this figure will be 2 into 8 cube divided by 12, and that can be transferred to this axis by that quantity plus area of this figure into distance between this centroidal x-axis and the parallel axis. So how can you calculate the distance? In this case, I know that from this x-axis to this particular point, the distance is nothing other than y2. So we can write it as Ig2xx plus A2 into y2 square. Now let us substitute the values. So you can see 10 into 2 cube by 12 b d cube by 12 plus area into y1 square or h1 square. Similarly, for second contribution, 2 into 8 cube by 12 plus area into 6 square. 6 is the y2 value. So we have transferred the moment of inertia from both the shapes. If in your question you have more simple shapes, you have to transfer all the values. And if you are getting a hollow shape, you have to take that contribution alone. Say suppose this rectangle was a hollow section. What we have to do? You have to, when you transfer this, that contribution should be completely considered as negative. Anyway, we will do one problem where we have a hollow section, and then maybe in some other lecture. So right now, we are just adding it up because all the shapes are positive values. There is no cutout sections. And this will finally come as 688 centimeter raised to 4. And don't forget to write the unit when you write for your examination. And this will give us the total moment of inertia about x-axis, the given x-axis. We have to also calculate the moment of inertia about y-axis. So how we can do that? When we were calculating Ix, we were taking the centroidal x-axis. Now we want to calculate the value of Iy. So we have to consider the centroidal y-axis. Why? Because when you use parallel axis theorem, the axis over which you need to calculate the moment of inertia should be parallel to the considered centroidal axis. So now in this case, what I will do is, I will first of all consider the centroidal y axis of my first figure. I will calculate the moment of inertia over there, then I will transfer that to the required axis which is parallel to this centroidal axis. So Ig1 yy plus a1 into x1 square. Why it is x1? Because I have my centroidal y axis here, and the distance between this axis and this y-axis is actually equal to what? It is equal to my x1 itself, and similarly for this it is equal to x2. So I will get the equations like this. When you substitute the values, vd cube by 12 plus a into h square and vd cube by 12 plus a into h square. So after simplification, you can see that the final value is coming as 688 centimeter raised to 4 itself. So in this case, the moment of inertia about x-axis and y-axis are same, and it is coming as 688 centimeter raised to 4. I hope you got an understanding on how to find out the moment of inertia of a composite section about a given axis. In the next lecture, we will be seeing a problem where we will work out the moment of inertia of a section about the centroidal axis, as well as we will include a hollow part in that, so that we will know what to do when we have a hollow section. Okay, so thank you for attending this section. We will see you in the next class.